Hello community! Today we talk about sensor array artificial intelligence. So what is it? Now we move from our language, from our large language model, where we have here given the languages to object, where we have a semantic, a syntax, a grammar, we have a vocabulary. Now we move over to some general data. We construct now a data array AI. So we will not here predict the next word in an autoregressive LLM, but we will predict missing data, missing global data, or something else. So what we dream of here is a capability of an AI system to reconstruct some complex spatial field from only sparse sensory data. So either you are here climate science, meteorology, or in medical imaging, or geophysics, seismology, you only have some sensors, you only have some images, some LiDAR data, some infrared observation, but you never have the complete sensory data that you would need. Or think about energy management. Here in smart grids, to efficiently manage and predict energy consumption and energy distribution. What if you do not have a sensor on each utility? If you do not have a sensor on each network node? We have sparse data, and we need to build with AI a complete understanding. Or look at it at financial modeling, analyzing real ultra-fast market trends, risk assessment, using a sparse data point from the Asian financial market, from the European financial market, from the American financial market, how they are interconnected. What if you only have some thousand data points and you are missing out a complete data field? This is the topic of today. So, and since we have an upcoming UN climate conference, hey, why not take here the example of AI for a global sensory array? As you can see here in the ocean between North and South America, there are a lot of sensors floating here in the ocean, measuring temperature, the wave height, salinity, pressure, and so on. But we only have 1,000 or maybe 10,000 sensor data for a complete ocean. So we're missing out a complete picture. So what we want to process here this sparse sensory data and reconstruct with the help of our AI system some complex spatial fields that engulf here maybe the complete planet Earth. Great. So clear aim defined, reconstruct entire global fields using only few sensor values. This is a visualization I tried to show you. Think about this is our system, this is our ecosystem. And you see we have here some array that have no sensory data. And then we have arrays where we have a lot of sensory data. Or maybe here we only have pressure data or atmospheric data, temperature data, and we're missing out the other parameter. So you see, this is here a real life scenario where you try to understand the complex system here in its time dependence. So how we do this? Now, you know, if you're a subscriber of this channel, hey, you know we need a spatial encoder for mapping here our spatial coordinates of our sensors to vectors. Then we need an attention-based encoder for transforming here our spatial encodings and our sensor values, the values that the sensor gives us, into a higher dimensional latent matrix space. And then we need an attention-based decoder for the output, for generating the output, reconstructing here our field values. And you might say, hey, this is nice. So we have here a latent sequence array here for some compact representation and non-local processing across input sequences. And you know, this is here the transformer architecture from our LLM, from our vision language model. We can use now our insight how an LLM works, how the different self-attention mechanisms interact together to build this system. So now we move from the LLM to a data array AI. Let me show you this in more detail. For example, you have here a value and have some mountains, and you see here, those are, for example, air pollution. And you want to monitor how is the air pollution situation. If you have, for example, an energy input from the sun, or you have a strong wind, or you have additional pollutants at specific local region, how does the whole system integrate? Now, the nice thing is and AI is now able to help us with this. To start, we have here from DeepMind, Google DeepMind, March 2022, a long time ago. They exactly examined this problem. This was before there was GPT-3 or GPT-4 or ChatGPT. This is from the old times. And they created here a general architecture for structured input and outputs. And they called this the Perceiver I/O. Now, this is a new encoder-decoder architecture based here on this. And it is handling here the sensory data through an attention mechanism for processing and reconstructing here what we need, our complex spatial data that have a complete description now of our system from just some sparse input sensory array data. Great. So if you want to have a deep dive, go to the original Perceiver model. This was also introduced, of course, by Google DeepMind here, to process large and heterogeneous input using transformer. It was designed to be modality agnostic. So we could process images, audio data, sensory data, numerical data, whatever we have. Then the Perceiver I/O that I just showed you built on this. And now we also integrate here, if you want, a modality agnostic output. So we have input, output, modality agnostic. Great. Think about the ocean. So let's say we have here a sensor network. Let's say this is somewhere here in the South Pacific. Maybe this here is around, I don't know, New Zealand. And this is here somewhere in Asia, some dense network here of sensory data. And then you can see the region in the ocean in this simulation where you almost have no data. But if we have, for example, a tectonic plate event happening, and we have waves traveling around the globe, and we have no sensory data. So we use now the sensory data that we have to understand the behavior here of the wave, for example, in these spatial locations. Great. Of course, another challenge is if we have satellite data, or we have real-time sensory data coming in every second, every minute, we have to integrate here real-time sensory data to understand here the ocean current, for example, or how a pollutant, if it's set free here, for example, in Florida, how it travels here the world, either in the fluid, in the water, maybe in the air, we have air pollution, and. And now, normally you have complex climate models that you have supercomputer and they crack the data. But the question is, can we use AI systems? Now what we know from the language modeling, think about how good ChatGPT is for the human language simulation and mimicry. Can we use this now here for other sensory data that are not words, the element, but numerical values? So now you know here in this picture we only have sparse sensor data. Maybe only 10 sensors in the whole ocean. So let me show you how good it could be approximated. Imagine we have a pipe. And in this pipe, we have two fluids. We have a blue fluid and a red fluid. And we mix it up, these two fluids, so we have a turbulent behavior. We have no laminar fluid dynamics within this tube. And then we put in 50 sensors at specific location in this tube. Let's say this tube is about, I don't know, 10 meters long and 1 meter wide. And on those 50 locations, we put our sensors so we understand at this very precise location in this tube, we can measure certain parameters of these two fluids. You see here at the bottom here, the ground truth. If we take here a laser and we here now monitor each water molecule here, this is here for a particular time interval, exactly here the distribution of the red and the blue fluid in our tube. And now the task is, if we have 25 sensor points or 50 sensor points or 300 sensor points in our tube, how good is our AI that we can reconstruct with our artificial intelligence here the real natural phenomena that happens in nature. So, as you can see, our 50 sensor locations, calculating now the whole volume of this tube, covers only 0.0006% here of the spatial area that is available to us here. So only 50 sensors here for the complete tube. And if you look now here at our AI computation, you see it is quite similar. So we have here the red fluids and the blue fluids, and you see there are similar patterns. Of course, if you increase now the sensor readout from 50 sensors to 300 sensors in the tube, you get even a better approximation. So you see, even with some small amount of sensors in the tube, with some ridiculous small spatial coverage, we can have here enough sparse sensory data to understand here the complete fluid system. And this is what we need. Now, here DeepMind and here Senseiver, this is here from Los Alamos research group, they said this is now what we call this. So the sensor receiver AI has some key components. We have two encoders. We have a spatial encoder, we have a attention-based encoder, and then we have the attention-based decoder. So what we do? This component, the first component, maps here the spatial coordinates to high-dimensional vector space. So this is exactly what we do with our LLM. We take the words or the tokens or the subword token or whatever tokenizer you have, and you map them in a high-dimensional 768-dimensional or 1024-dimensional vector space. This translates here the geometric information of the sensor location in a format that the neural network can process. This is absolutely identical what we do here in the language model. We have here similar sentences and we put them in places in our vector space that are close by. Beautiful. Then, in our transform architecture, we have now self-attention coming in. So, leveraging now the attention mechanism, this encoder transforms here the spatial encodings and the values from our sensors. So we have the location of our sensors, where they are in the tube, and the specific sensor values about temperature, salinity, about the pressure, about whatever. And we integrate them nowadays in our matrix space. This is crucial for capturing the relation and dependencies, also time dependencies, between the different sensor readings and their location. And then, if we have this encoded, we just do the reverse. So we do the attention-based decoder step. You know this from our LLM system, from our transform architecture. Now the decoder uses a Latin matrix to output here the reconstructed field values. At which point was the red fluid, at which point was the blue fluid. It essentially translates here the process sensor data back here into a comprehensive spatial field, which could represent various physical phenomena. And this is exactly what we need. We have now the original behavior of the system, and then what we do, like in the LLM, we calculate here a specific loss function. It is a very easy loss function in our example. So, and you have backprop and forward parsing and everything that we know from our LLMs. And the same happens here. The only difference is that our objects are not tokens from words, but here we have numerical values that tell us what numerical manifolds our system can approximate or can inherit. So beautiful. So the primary function here of this sensor receiver is to reconstruct your entire global fields using only some few sensor values, our sparse sensor array data. This is useful when we only have some limited amount of sensor, or in some area we have no sensor at all. Great. So if you look at this from an information theoretical perspective, this sparse sensing phenomenon that we are now trying to solve here is nothing more than an inverse modeling problem that maps here the sparse low-dimensional measurement to a high-dimensional state. Great. So very easy if you think here about the planetary ecosystem. Maybe you only think about the water ecosystem. Maybe you think about the air ecosystem. But of course, you have here that water evaporates, becomes here, changes the state, the aggregate state. You have a dynamic, depends here on the climate, depends on the temperature, on the pressure, and then you have whatever heat is radiated here from the continents. So the complexity of the ecosystem that you have, we try to map this into this high-dimensional space so that our AI can find some patterns within this state. And then if we reduce it here to the simple output space, those patterns become available for us to examine. Great. Now we have two ways to think about this. Either we have here in fluid dynamics or diffusion theory in theoretical physics, we have an equation, we have a mathematical equation. And I can tell you, hey, if this is this, and this parameter, and this coefficient, and the Brownian motion, and we have some infinitesimal increments, and yes, this is it about the time interval, I can give you here an equation where we can solve this equation for a particular system with here specific boundary condition, with specific initial conditions of the system. This would be here the theoretical physics approach, or if you put all this equation into a supercomputer and you just give it all the start parameters here and the boundary condition. Or, and this is what we try now in this video, what is also here a research topic, I just give here the sensory data of this system to the AI. So instead of a single formula with an analytical solution that I have to solve for every molecule in the complete system, I describe here, if you want, in this numerical sensory data array, the process that is happening in the system. And a third solution would be that I say, okay, here, this is molecule number 1512, and it is now approaching molecule 5716, and it is right next to molecule 25808. But you see, a language description does not make sense. A pure mathematical, analytical description would need extreme compute power. And this is now, if you want, the third way that we give here the complete system to the AI, and the AI tries to understand here the critical component of the system and understands here the interrelation between the different parameters of the system that can change and that have here an influence on the system output. Beautiful. So what we have a data-based reality here of a single process. I showed you this on a diffusion process. So you can now understand this either on a mechanical level, on a molecular level, whatever you want. You can program this here as an input from few sensory data to here our AI. So we have a data sensory array input to our system. Yeah, as I showed you in this beautiful video, that there's a solution if you have a pre-trained model. If you want to add characteristics and functionalities, we can do this now with LoRA adapters, where only the fine-tuning of the LoRA adapter layer is happening, and the pre-trained model, the weights, the tensor weights here are frozen. And I showed you that we can do this for multiple LoRA adapter. If you have 100 product description and you have an upcoming sales information for your company, and you want to program the perfect customer interface AI, you can do this weekly. You can update here the blades every month. If you have special promotion, or if you want to optimize for cross-selling or upselling, you can do this simply here with some adapter. You can switch on and switch off. But the pre-trained model, the main big huge model, is frozen. It stays the same. But we learn new behavior here with the LoRA adapter. And now here, you understand, the idea is now we can do the same. We can configure now our perfect NOAA AI here for the oceanic and atmospheric administration AI system. So we have here the global oceanic fluid dynamics of our planet here in detail. And then we just train for special events, like an underwater volcano eruption, or for some specific diffusion processes of pollutants that enter here. Think about the Gulf of Mexico. If there's an oil spill, what happens? We can take at least here the historic data and show how the oil moved here in the Gulf of Mexico and what happened. Or we have a mathematical simulation and put this as an input data array to our AI. We can have What happens if there happens landslides above ground, but also underwater landslides? What about plate tectonic events that happen at the bottom of the ocean? What is exactly here our theory? You can update this, you can fine-tune this, or about wave oscillation in specific geographic regions. So you see, you can build here your model that takes into account all of those different effects, and you do not have to fine-tune and pre-train everything, but you can do this here, and this is the beauty, as I showed you in the last video here, on the LoRa adapter. Great. Yes. In the video here about the stable diffusion optimization that are happening now last week here with an LCM LoRa, so we do not have just the LoRa adapter modules, but we have now here the LCM LoRa, and I showed you here, you can very easily set the adapters together, combine the LoRas. You set adapter, your first adapter, your second adapter. We already have here the mathematical code implementation on Hugging Face, for example, for image manipulation for stable diffusion XL. With our LoRa models, we can take LCM LoRa models or the classical LoRa models, and we can build this here on visual data already. And now it would be just to go from a two-dimensional visual data to a three-dimensional physical system. Great. All of this is here in this publication by Nature Machine Intelligence. You know, Nature is behind a paywall, so I cannot show you here the complete study for obvious reason. But just to tell you, if something happens in Nature, it takes 1 year. You see, publication was received here the 1st November 2022. It was accepted by Nature after the peer reviewing where other university professors looked at this and validated it at September 21st, 2023. And it was published online just for me some days ago, November 6th, 2023. So it took from November 1st, 2022 to November 6th, 2023, 1 year to be validated and then finally published behind a paywall where the normal audience has no access rights. But if you're a student, you go to your university, you have access to the Nature publications, hopefully through your university, exactly like I do. So please, this is the HTTPS link. If this is behind a paywall, sometimes they open the paywall for special events. But yeah, this is it, just to make sure. And reading this Nature publication, I get all the ideas for this video. So this is the reason why I did this video. And the ideas from this video are responsible for what I just showed you. But I also explained you the content here of this Nature article. Great, and here we are. We want to understand if we only have some 1,000 sensors here floating around in the ocean, and maybe just some 100,000 sensors that we have on land, on the continent, for air quality, air pollution, temperature, humidity, whatever. We want to understand here our global ecosystem. So going here from some sparse data, some sparse sensor arrays that we have, to understand here the complete planetary system. And now with these insights that we have in the large language model and all the research that happened there and the computer optimization, think about scaling LoRa, here about the memory management optimization here on the NVIDIA data center GPUs for the pseudokernel optimization. If we apply this now here, we take this that exists on the LLM and we move it over to the data AI system. This is something I call transfer learning. This would be amazing, and this would be a real benefit here to understand climate change and finally come a step closer to understand here the complete global ecosystem. So you see, understanding AI system, even as simple as an LLM or a visual language model or a robotic model system, if we understand the mathematics, if we understand the principle, how it is coded, how we can optimize here each and every step, we can use this then at a later time and apply it here for our data sensory array where we can reconstruct some global ecosystem. I hope you find it also interesting. I am fascinated by this. I read the article, I had all these ideas, and I wanted to make a video to share my ideas, my knowledge. And I want to show you, if you understand what's going on and not just copy the code and apply it without understanding here the insights, you can build new systems that are absolutely amazing. This is it for today. I hope it was informative, and it would be great to see you in my next video.